Okay, thank you very much for having me. So let's get started so you can see. Should be able to see my screen now. That's what we tested earlier.
Looks great, Mai.
Good, good. Okay, so first of all, thank you all for being here and joining me here for my talk. I'll be telling you about stellar symphonies and how we can use those to learn about what's taking place inside of stars. So first of all, something that's always never fails to fascinate me and is one important message that I want you to take away from this talk. So if you don't remember anything else, maybe you'll just remember this. And that is all that we know about stars, we know from studying the light that they emit. Okay? So how is this important? Well, we can't that easily just travel to where the stars are and have a good look at them and study their properties. Why is that? They're quite far away. So if you look at the nearest star, that's not the sun. So yeah, the nearest star that we have is the sun. So we'll ignore that for now. The second nearest one is called Proxima Centauri. And let's say we have quite an amazing car that's able to drive in space. And this car is able to travel at the speed of light. If we try to drive from the Earth to Proxima Centauri, that would take us a bit more than 4 years if we can travel at the speed of light. Let's say instead we're limited to speed restrictions, such as the ones on the Californian highways. And so instead, it would take us about 44 million years to actually travel to the nearest star. So instead, what we have to do, we have to study the light of stars. And the places where this light and the energy of the stars are generated is mainly in the cores of the stars. So throughout the majority of their lives, the energy that is produced inside of stars is generated from the nuclear reactions where you fuse hydrogen into helium. So that's, astronomers call that as nuclear burning of hydrogen into helium. Okay, so 90% of their lives, stars live in this way, very quietly, burning hydrogen to helium. And during this time, astronomers have a way that we like to characterize stars and classifying stars, putting stars in boxes, and we do so according to a letter system that we remember by this one phrase called "Oh, be a fine girl or guy, kiss me." Okay, so those are the letters O, B, A, F, G, K, and M. What this actually is a temperature scale. So as we go from the right in this diagram towards the left, the stars become hotter. In this diagram, you see down here this yellow star would correspond to the sun. So the sun is a G-type star. It weighs 1 solar mass. So as astronomers, we weigh stars according to the mass of the sun. So in comparison, if we look at these more massive stars, as we call them, the mass of these stars are above 3 solar masses. Okay? Something you might also have noticed by looking at this diagram is as we go from right, the stars are redder and becomes bluer as we go towards the left. That's also an effect of temperature. So you can look at the analogy of a candle. The flame of the candle, the place where it is hotter, is here at the base where it's blue, and at the top part where it's yellow-red, the candle is cooler. Okay, so if we have a blue star, we know that it's warmer than a red one. Okay, so if we go outside, you'll be able to go now and look at the night sky, look at the stars, and try to look at what colors they have. And now you'll know whether the star is a hot star or a cool star. So one example, if you go out and look at the constellation called Orion, we have in one of the shoulder, we have Betelgeuse, which is a red star. So we know Betelgeuse is cooler than Rigel, which is blue-white in color instead. So that's one immediate knowledge we can get just from studying the light and the color of the light of the stars. Now, the stars that I'm personally very interested in studying are these higher mass stars. the O and B type stars, which we also refer to as the chemical factories of the universe. Well, throughout their lives and deaths, they're responsible for producing heavy elements, which they feed back to their environments, both through their strong stellar winds and also later supernova explosions. So in this way, they chemically enrich their environments, meaning that stars that are formed after them in planetary systems will be impacted by any chemical evolution that these stars have gone through before. Okay. Now, what these stars have in common, these O and B type stars, is their internal structure. So if we have a bit of a look at that, what we have here on the left is a 3D model of a B-type star in this case. And what we do with the interior of the star is we split it into 3 different regions. So in the core, we have what we call a convective core, meaning that the energy is transported away by convection. So you can look at convection a bit in the same way as if you have a boiling pot of water. The bubbles moving up and down are similar to convection in this case. In the envelope, we have a radiative envelope, so energy is transported away by radiation. And in between, we have sort of a transition layer. Okay. Now, the very important part that we have here is exactly this convective core inside of the stars. Because of this convective motion, the stars are very good at mixing the material that's inside of the cores. Okay. So all the hydrogen we have inside the core, we can use as fuel during the majority of the lives of these stars. That also means if we have any additional mixing of the chemical elements that takes place in the envelope and in the transition region of the star, that means we can bring new hydrogen fuel into the core and thereby get the stars to live longer than we would normally expect. These kind of mixing we represent by what we call mixing diagrams that shows you the efficiency of the mixing as we go from the center towards the surface of the star. We color these regions of the mixing efficiency according to the 3 regions I mentioned before. So gray is the convective core region, blue is the transition region, and green is the radiative envelope. So in the core, we have very high efficient mixing values because it's convective. Okay. Now, one big problem that we have is that we actually don't know exactly what these internal mixing profiles, as we call them, these diagrams, what they look like for these stars. We don't know what the shape looks like or how efficient the mixing inside the star is. So that has a very big impact. That's going to change the age of your star. So we can't estimate that for certain. Another issue that we have is that while the lives of stars are governed mainly what's taking place in their interiors, what we're observing is their surface. So 100 years ago, a question was raised by Sir Arthur Eddington, which was, what kind of appliance, what instrument can we use, what methods can we use to look into the stars and get some constraints on what conditions that we have inside. So for this, astronomers have taken inspiration from a geologist, geophysicist, who study the waves inside of planets, okay? So if you look at the Earth, if an earthquake takes place, what happens is that this earthquake generates waves that travels throughout the interior of the Earth. As these waves hit regions with lower and higher densities, they will bend, meaning that they reach the surface at different times that you would normally expect. Okay, so we can draw lines here from where the earthquake took place, following how the waves travel, and draw diagrams such as these, just to where the lines here in this case represent the travel path of these waves inside the Earth. And so the idea is what geologists do is place seismometers around the Earth and measure the arrival times of these waves that are generated by earthquakes. And from that, you can infer information about the interior structure of planets and the Earth. So as it turns out, stars in a similar way also have waves. So this is again a 3D simulation of a star where we have the convective core like before that are generating waves, which we refer to as internal gravity waves in this case. So the different colors here correspond to temperature fluctuations caused by these waves, where brighter region corresponds to hotter temperatures and dark or purple are cooler regions. And as you see, these waves causes temperature fluctuations at the surface, which translates to variations in the brightness of the star. So what are these methods called? Well, if you study planets, you're using seismology to study waves, whereas for stars, we refer to the study of waves as astroseismology. Now, one immediate thing that we can learn from studying waves of stars and listening to the music that the stars are generating is something about the sizes of the stars themselves. So in this case, I like to draw the analogy from the case where we have violins and a cello. So for a violin, if you play a violin, you'll know, or if you've listened to one before, that the sounds are higher. That is, the frequencies, the sounds that the violin make are higher than the ones that the cello make, that are deeper. Similarly for stars, a smaller star will have higher frequency, higher sounds, that their oscillations, that the waves are making, compared to larger stars. What does this actually sound like for real stars? So let's say for the sun, if we observe the oscillations that the sun have, observe the frequencies and transfer them to a range where we can actually hear it with our normal ears, the music that the sun is creating sounds like this. Now, if we go to a larger star, we'll notice that the sound is deeper. And in comparison, also if we look at a smaller star, so the sound is much higher. Okay? So just from listening to the music of these stars, we can infer something about the sizes. So one thing we as astroseismologists, like I do, is that we try to characterize these oscillations that the stars have. And so the analogy that we look at in this case is that if you have oscillations in one dimension, then that corresponds to an oscillation you get if you pluck a guitar string. Okay? In 2D, in 2 dimensions, it's the same as the head of a drum, whereas in 3D, we have a sphere, so that's our star. Now, depending on the frequency on an oscillation, you will get different points along this string where the string does not move. It's standing still. So that's what we call nodes. And for stars, we use these nodes to characterize the pulsations, the oscillations that they have. So for stars, we use 3 different kinds of quantum numbers. One is the number L, that's the number of surface nodes in white, shown in this diagram. So blue parts of the star is parts where the star is moving outwards, and red, the star is moving inwards, and in white is where the star is not moving at all. Okay? So for the L value gives it the number of nodes on the surface. M gives you the number of nodes that are crossing the equator. And finally, the radial order N tells you gives you the number of nodes inside of the stars. Okay? So those are the 3 quantum numbers that we're using. Finally, the types of oscillations that I'm studying are referred to as gravity modes. Okay? So these gravity mode oscillations have a high probing power near the core of the star, meaning that they have a lot of information, if we can observe them, about what's taking place near the core of the star in particular. Now, these oscillations have some very distinct properties, and one of those is that they is related to the periods of the oscillations. So if we look here at the 3 different types of oscillations, where we have the same number of surface nodes in all 3 of them, same number of surface nodes crossing the equator, but the only difference is the number of internal nodes, the radial orders of these oscillations. We can refer to these, the periods of these oscillations, as P1, P2, P3. And if we calculate the differences between the periods of these oscillations, so that's this delta P, that's also called period spacing, what we find is the differences in period between P1 and P2 is similar to the differences period between P3 and P2, okay? And so forth. So what this means is that if we take these period spacing values and plot them as a function of period, we expect to get this a straight line in this kind of period spacing diagram, okay? So in the case where the star is not rotating, where the chemical structure is the same throughout, we expect these period spacing patterns to be completely flat. And to help guide the eye, we draw a line between these different measurements of the period spacings. As it turns out, if we have a rotating star that's not chemically homogeneous, these patterns change, and we can use that to infer information about the interiors of these types of stars. So if we go from these theoretical period spacing patterns and try to look at examples where we've actually observed them, then these are 7 examples of observed period spacing patterns that have been identified in a specific type of oscillators that are called slowly pulsating B-type stars. So that's up in the high mass star regime we're at. Now, the first thing that we can infer from these period spacing patterns is related to this slope of the pattern. So in the case that the stars are rotating, what happens is that the periods of the oscillations become a smaller that corresponds to a higher frequency, and also the patterns get tilted as well. Okay, so if you try to listen to the sounds of these patterns, we can do that too. Starting from the top one, you will hear, as we move downwards, the sound that the patterns make become higher, okay? And that's caused by the rotation. And if we combine them all, we can listen to a symphony of these patterns. Now, additional information that we get is by measuring the average period spacing value of these patterns. That tells you something about the mass and the age of the star. So this average value will shift up and down depending on the mass and age. And finally, the exact shape of these patterns in these period spacing diagrams depends also on the age as well as the internal mixing of the star. So what we've managed to do is actually to try to study these period spacing patterns of 26 of such slowly pulsating B-type stars. And from this, we've managed to infer what the internal mixing profiles looks like for these 26 stars. So in this case, we're again looking at internal mixing diagrams. We're showing the mixing efficiency on the y-axis and the position inside the star, where we go from core towards the surface. And in each one of these diagrams, you will see a profile, and the number of profiles in a given diagram corresponds to the number of stars that prefer that kind of configuration shape of that profile. So what you see is there's a large diversity in the mixing of these stars, which is very interesting. And for the first time, we've actually been able to try to infer what these internal mixing profiles looks like for such a large sample of stars at once. One final thing I wanted to mention is that these results were actually based on a stellar structure and evolution code that's developed here at the KITP. So that's very important in this case. That's allowed us to try to compare the observations to our theoretical predictions. And finally, I hope you can take away from this, again, that you can learn a lot just from studying the lights of stars, and astroseismology is a really, really cool field to study. Okay. Okay, and with that, I'd be happy to take any questions that you might have.
Thank you, Mai.